Last lecture. I have a flight to catch which does not interfere with our actual time of an hour and a half. I think I can go to an hour 45, but if I went to 2 hours, I'm starting to really push it for my flight. So hard cut off, I'll just go, so you don't have to worry, it will all be over soon. All right. I decided I would just start today with drawing a few plots on the board so that I didn't have to sort of do them, as we're discussing. So we've talked. We went through the evidence of dark matter. We went through some of the properties of dark matter last time, and so now we want to talk about some of the models of dark matter. What could it be? And if it is what it is, then how do we see it? How do we find it? Again, it's a large subject. I cannot possibly cover all of the areas that I can, but I do want to just touch on a number of sort of qualitatively different candidates and sort of the origin of where these candidates would come from. What's the mechanism? So let's start at the low end, down at 10 to the 22 eV. So this, as we've already learned from last time, has to be a scalar. And by the time you're at this level of mass of a scalar, you're not talking about an individual particle, but a collective set of coherent excitations. The classic example of this, of course, is the Axiom. And I had a wonderful set of notes ready to go for axion physics. Honestly, there have been great talks about axions already. You can go and look at Nathaniel's lectures from last year. There is also some wonderful notes from Matt McCullough from a year before that, which explain these things in great detail. So if you want to learn about axions as a solution to the strong CP problem, I encourage you to go look there. For our purposes, I only want to talk about axions as dark matter. And for that, whether it's an axion that solves the strong CP problem or is simply an axion-like particle, that's equivalent. So axions have the property that they're Goldstone bosons. Now we know what that is, right? A spontaneously broken symmetry from which there is a massless excitation. But, and as we've been seeing this over and over again in many of the instances as we've been talking, it's a spontaneously broken symmetry that also has an explicit breaking due to QCD. And the explicit breaking is what gives it its mass. Just like, in some sense, with the explicit breaking from Yukawa couplings gave mass to the pions. Okay. From a cosmological point of view, the axion basically does the following. So the axion initially starts as a scalar field that is approximately sort of flat. It sort of may remind you a little bit of what happens with an inflaton. And so it actually sort of, if you want to plot it in the space of the equation of state parameter and the density. So the equation of state, of course, in this case is really just T minus V over T plus V. The energy minus the potential, the energy plus the potential, to a good approximation. So the extent to which this sort of setup is going to be valid is where, once the Hubble scale becomes lower than approximately the mass of the axion, then the axion will begin to behave like a substance that we're all very familiar with. And it's interesting, there's a set of lectures by David Marsh that you can look at, and he actually has these plots in there. It's actually a wonderful review of axions if that's, again, of your particular interest. So the picture is that initially the axion is dominated from the perspective of Hubble expansion, and after we've already sort of generated a little bit of mass, it's essentially dominated by its potential. And so something that is dominated by its potential and not its kinetic energy, obviously W is -1, as we know from inflaton story. So it sort of sits like this, and then there's a point at which it sort of falls off and it starts doing coherent oscillations about the minimum, and as it does those coherent oscillations, you're basically sloshing your energy back and forth between kinetic energy and potential energy. And when you do that, you get this wonderful behavior of what the equation of state parameter looks like. If you average this, just write it here, when the potential is specifically mass squared phi squared, then this average, chalk, is 0. So, and that's one of the special properties of scalars that have just mass and no other terms in the potential. Okay, it's a special property of that this happens. So, and of course, what's famous about something with W equal to 0? It's us. Non-relativistic matter, right? This is the same equation of state parameter as non-relativistic matter. So the origin of why axions provide a potential dark matter candidate is sort of this interesting fact about a specific kind of potential that is acquired for the axion, and this averaging that you get for the equation of state. Of course, this is exactly what happens after you're dominated by the mass. So that say what?
What do you average over?
In effect, you're averaging over whether the energy is in kinetic or potential. So you're basically doing this average for this scalar field. Yeah, and when you do that, then for a potential that has just a mass term, this is what you get. If it's not a mass term, you get something else. Okay, just to be clear. Yeah.
Is this average like a quadrant average, like a half interval, or is it like a time average where you average over time space?
It's like a time average.
Okay.
Yeah. So this is dropping here just like matter. So this is the basic principle why axions potentially provide a candidate for dark matter, and after that, all you really have to do is to compute where the abundance comes from. Okay, and the abundance of axions is, I would say, an active subject. There is the standard story, sort of known as the misalignment mechanism. And essentially, if you require the axion energy density to match what you need for cosmology, then there is a relationship between the parameters of this potential that you put in here and basically the mass or the effective decay constant. And so then you can actually predict what the axion mass would be as it falls out. I could write an expression. You can look it up. It's not too difficult to find. Roughly speaking, mass is on the order of, again, it depends in detail on whether you're considering specifically an axion that solves the strong CP problem, or whether you're considering a general axion-like particle. If it were to solve the strong CP problem, the mass is something like 10 to the minus 5 to the minus 6 eV. It's in that ballpark. Okay. And that's about the mass that you need to make this work. So that's not here, that's sort of maybe here, but it is well within this sort of territory of the axion behaving like a coherent scalar field. Okay. Oh, and last comment about this. I'm not going to talk more about axions today. But I will say that this is a really active area. It's funny because this is an area of physics that has been around for 30-odd years in some form, and yet only in the past 5 to 7 years or so there have been a number of maybe a little longer, maybe 10 years. There have been a number of experiments, including one or two here in Mainz, that are specifically searching for the axion through its effective interactions that are there. And so it's a very interesting subject to get into, but again, given the time, I'm going to have to move on. Okay. But I wanted to at least mention this is one potential possibility for dark matter. Okay, moving up in dark matter mass, as I walk to your right, let's now sort of focus on scales, maybe sort of keV-ish, though it's, at this point, the specific scale that I'm talking about is not particularly important here, but this is, I would say the next mechanism I'll talk about is very typical for scales from, say, keV up to maybe MeV or low GeV or so. And here now, I really am trying to plot the, I really want to plot something a little bit different than what I plotted over there. Let's plot the number density per co-moving volume. I could write a symbol, but everyone's symbol is defined differently, so let's just write the text. This is a candidate that was never in thermal equilibrium. Never in, but it still couples to the standard model. So that means that the standard model was hot at some point, lots of particles. There's some tiny coupling. It has to be small, or otherwise it would have been in thermal equilibrium. So there's some small coupling, or let's call it a tiny coupling, to standard model. So there's some standard model, some tiny coupling. It's not in thermal equilibrium, but the process is occurring, albeit rarely. The notion of standard model processes annihilating and going into whatever this other particle is, this dark matter candidate. And since that dark matter doesn't talk to us with any strength that allows it to be in thermal equilibrium, then it just means that all you have to do is to integrate over the time that you have in the universe, and you will slowly increase the abundance of that particle. You get the greatest rate of change of abundance. The largest slope is always at early times, high temperatures, because that's where these processes are going to dominate most. If you have something that is very suppressed interaction, then once you compute a cross-section, you're always putting powers of temperature, into the numerator, and so effectively you have to go to high temperatures to get a high rate. And then you go to later times, you get lower temperatures, and that's why this abundance then sort of levels off. So this is known as freeze-in. So it is another possibility for where dark matter could come from. It is often employed to obtain the correct abundance of light dark matter, specifically dark matter sub-GeV. Okay, so if we maybe put it the GeV scale here, down on this end, this is common. Not absolutely the only way, but it is one of the ways that is viable for some reasonable fraction of the parameter space that light dark matter enthusiasts would like to explore. Okay. So freeze-in. Good. The next one, hopefully, is familiar. So here I have the same. I'm plotting the same thing, and now the difference you can see between these two curves, and again, time is going this way, temperature is going down in the universe. So you can see the difference is, whereas this was never in thermal equilibrium, so it starts with a arbitrarily small sort of density, this is in thermal equilibrium with the standard model, and So as a consequence, whatever the standard model processors are doing, you can annihilate into the dark matter, and the dark matter can annihilate back into the standard model. And these processes go back and forth very rapidly. Once you cross a temperature, so let's call this 1 over T, of order very roughly, right, so this is time, a particular time that is 1 over the temperature, which is 1 over the mass of the particle here, then you change from this species being relativistic and scaling with radiation, and then it eventually becomes non-relativistic and gets a Boltzmann suppression. Right? So you get the standard exponent of minus m over t. And if it stayed in thermal equilibrium forever, then it would just get an exponentially suppressed abundance. But of course, this can only survive for so long because there's some interaction rate with the standard model that eventually that interaction rate freezes out. And basically we say that when the Hubble expansion parameter, see if I get this straight, when the interaction rate of the particles drops below the Hubble expansion rate, so this is a 1 over time, when this rate drops below the Hubble expansion, then we say that whatever you're left with in that species just stops interacting and it freezes out, and we get an abundance of dark matter here. Okay. So freeze out has been a common mechanism to try to explain the origin of dark matter for a long time. It does have a number of features to it that are somewhat distinct from the others, but okay, it is one more mechanism. So still marching up now in mass, and at this point, the next thing I'm talking about, in principle, could start from maybe some several GeV or a GeV scale or so, and go above, but I'm putting it over on this board because it's one of the few ways to try to get north of the TeVs, north of the 100 TeV scale, a scale we'll talk about in a moment. And I actually don't really know what I'm supposed to draw here, so I just drew something with lots of colors. Okay, but what I am trying to draw is the abundance of 2 different kinds of species. So one of them is baryons, so matter, and one of them is antibaryons. And I put this on the plot, but of course, in reality, in the standard thermal expansion history of the universe, this is really incredibly tiny. Right? The freeze-out abundance of antibaryons is incredibly tiny because, of course, there's so many, even though, as Misha has been telling us, there's a baryon asymmetry, this tiny 1 part in 10 to the 10 difference between baryons and antibaryons. And once we reached approximately the mass of the proton, these things all found each other. All the baryons and antibaryons found each other. They annihilated, went away into photons and other stuff. Except for that one little part in 10 to the 10, and 1 little part in 10 to the 10 froze out to become these. And all of the other antibaryons, well, if there was any antibaryon around, it was always completely overwhelmed by the baryons, and so it could find one and go away. So we're left with, as I said, an incredibly tiny abundance of antibaryons. So it shouldn't really even be on this plot. So this is a asymmetric, A-S-Y, origin of a species specifically baryons. And you can imagine the same thing or something similar to it happens for dark matter, in that dark matter could have a conserved quantum number. There could be some early slight difference between dark number and dark anti-number, a slight asymmetry. And if this asymmetry is not violated by, effects, then as that thing freezes out, you will end up with some abundance of, shall we call it, dark matter, and all of the anti-dark matter gets suppressed. And it's a qualitatively different mechanism because, right, these, where these curves are is quite different from where this is supposed to be. So as I say, exactly what I'm supposed to draw here is a little bit unclear, but I had to draw something because I was doing plots. So, okay, all right. At first, this seems a little bit ad hoc because you might say, well, we don't even know the origin of the baryon asymmetry. So really, you're going to tell me that there's yet another asymmetry in the universe, and that's what gets how we get baryon number? If it were that, then yeah, it wouldn't be very compelling. But of course, there are possibilities where you can link the baryon asymmetry to the dark matter asymmetry. Let me just make just a couple of comments about that because I probably won't do any more of this again. So as we know, sphalerons, which if we didn't already have Mish's lectures, I'd have to explain what those are, but I don't have to now. You know what they are. Sphalerons, the non-perturbative solutions at high temperature that violate the global symmetry B plus L in the standard model, are what allow you to transfer a lepton number asymmetry back into a baryon number asymmetry, or vice versa. So this is one of the ways, at least for high-scale leptogenesis, is the way to be able to acquire a baryon asymmetry in a very elegant way. Right? You start with one number, and then the sphalerons reprocess that into baryon number. And that's effective all the way down to the temperature at which sphalerons decouple, which is something on the order of the electroweak scale. He might have given a number, and I don't remember, but let's just call it V. It's close enough for our purposes, okay? But it's on that order. So the reason, so B plus L is violated, but B minus L, right, is conserved. Right? So B minus L is a good symmetry, right, of the standard model. So now if I have a new dark matter number, and I imagine that it mixes in some way with baryon and lepton number, the thing that's conserved could be some number, some B minus L plus some numerical coefficient that depends on the model times dark matter number. And then what sphalerons will do is violate not B plus L anymore, but it'll be B plus L plus or minus some other number times D. Okay. So now what will happen is, if you start with, say, a lepton number asymmetry, it could be that then sphalerons will reprocess that into a baryon number, and then also simultaneously reprocess it into some fixed amount of dark matter number. And so that could provide then the origin of why rho dark matter is rho matter. These mechanisms, all of these, freeze out, freeze in, and misalignment, all obtain the dark matter abundance basically through an accident. It's a numerical accident, right? The abundance of baryons is due to an asymmetry, and yet over here, you're getting dark matter is coming out because you just happen to have annihilated just at the right rate so as to get an amount of, dark matter that happens to match this value here. So it just happens to match matter, but there was no reason for it to do that. Could have been much larger, much smaller. Same thing here, same thing there. All I have to do is adjust parameters, and I can get whatever abundance I want. Well, okay, within reason, right? But I can get wildly different abundances. This mechanism is interesting precisely because it could link these things together. Now, realizing a model of this is tricky because I sort of drew these lines of dark matter and anti-dark matter, but you could imagine that in addition to getting a certain amount of asymmetric dark matter out of some mechanism here, there could also be a certain amount, there can be a certain amount of anti-dark matter as well, just through normal freeze-out, okay? And if normal freeze-out led to a larger abundance than the asymmetry, then this doesn't even, it's not even an effective mechanism, right? So one of the requirements to make this thing go usually is that you need the annihilation, A-N-N-I-H-I-L, of dark matter plus dark matter bar, right? It has to be something that has a conserved quantum number into standard model. Say, this had better be strong. Right? It had better be a large rate, potentially strongly coupled. And by this, I don't mean strongly coupled to the standard model per se, but I mean that the dark matter needs to find itself easily and then annihilate into stuff. The easiest way to do that might be exactly, let's just write this. The easiest way to do that would be to follow what the standard model does. Neutron plus an anti-neutron goes into a whole bunch of pions, right? And then the pions decay into whatever they're going to do. And right, this is a strong process, right? It has a large cross section. So it annihilates away any would-be thermal abundance of neutrons. If, for example, we had a universe in which the neutron was stable, then of course we could have produced a population from this. Of course, it's not stable, but if it had been stable, you could have done this. But in fact, these things are already have a strong interaction annihilating into pions, and so you really, it's very effective to get rid of any symmetric abundance this way. So these theories, I think, most naturally tend to fall within cases where dark matter is itself somehow connected to a strongly coupled sector. And maybe that's this is sort of maybe the closest thing I can say that sort of best sort of impacts some other areas that we've been talking about at the school, right, with non-perturbative physics. So there's a whole number of people who study these kinds of theories. I've done a little bit of this. So has Michele Reddy and lots of others. There's a Yang Bai. Okay, I could go on. There's like this small little group of people who. Okay, it's not that small, but there's a smaller than over there. Okay, smaller than all of the people studying that stuff. There's people who sort of study this and see what can you make of it. The reason I put it on this side of the board is because I'm going to talk about this in just a moment, but the highest scale that you can realize out of freeze out, which I'll show you in a moment, is about 100 TeV. Okay, and I'll show you exactly where that comes from in just a moment. But so you can ask, well, is that then the ultimate bound on dark matter? That is with primordial black holes setting that aside, which I've already sort of made some arguments about. It probably can't be all the dark matter, and it has issues, and where you get the abundance of primordial black holes is really mysterious. Okay, anyway, that's a whole other story which one could go into. Anyway, I have opinions. Okay, anyway, off we go. I've written papers about this. Anyway, fine, doesn't matter. The question is, what can you do above 100 TeV? And from the perspective of single particles, this is the limit that you can get to. But you could imagine that you produce some single particle out of say an asymmetric origin. So you produce a bunch of dark matter states that are strongly coupled. But then it could be that if this dark matter state is also strongly coupled to its relative, such as the neutron is strongly coupled to the proton, then they could start globbing together into dark nuclei. Well, when I say dark nuclei, here I really have in mind something very, very analogous to what happens with nuclei of the standard model. But you could live up here with something like that. This is also called, I think it's called dark nuggets. So nuggets now is sort of meant to be almost macroscopic numbers of dark states all glommed together. Okay. So obviously, for any of these processes to go, the dark matter had better be very strongly coupled to itself, so as to sort of glob together. And that sort of also leads to this notion that probably the dark matter with its anti-dark matter, this is probably also strongly coupled, so it's consistent with not getting a thermal abundance, and so forth. So, and this, as I said, is sort of most naturally understood from an origin that comes from an asymmetry. So we have populated the entire dark matter mass spectrum from 10 to the minus whatever eV, some tiny, tiny scale, and we can populate it all the way up to far north of 100 TeV. Though in each of these cases, really there's only the mechanism by which we have to arrive at dark matter is probably one of the types that I'm showing. So freeze out doesn't work here. Freeze in is not going to work sort of here. It's not strongly coupled, and so forth. So that's how these scales also tend to break down into the different mechanisms by which you could see the origin of dark matter.
Sorry.
Yep.
Did you say that if dark matter is made of bound state
Yep.
or strongly coupled sector, then the abundance is not fixed by thermal equilibrium?
So it's not set by thermal equilibrium in the sense that thermal equilibrium will only set the symmetric abundance of dark matter plus anti-dark matter. The dark matter number, the difference between those two numbers, is set by whatever the asymmetry is. Yeah, and that asymmetry is related to however dark matter number is somehow mixing with our real baryon number and our real lepton number. Yeah. That makes sense? The one thing that makes this a little bit confusing is I'm sort of suggesting some sort of freeze out here, but it's not really freeze out per se. What's happening instead is there is a thing that's freezing out. What's freezing out is failerons. In this picture in the back of my mind, what's freezing out are electroweak failerons. Because failerons are no longer effective once we drop to temperatures below V. And so this ability to move back and forth between B, L, and D number is gone once we've dropped below the temperatures of the electroweak scale. If indeed this is the mechanism that's keeping all of these things together.
Maybe it is related, but I was asking for strongly coupled, not for asymmetric, but maybe it is related.
Sorry, say again?
I was asking for strongly coupled dark sector.
Yes?
And but you are telling me about the asymmetric dark matter, right?
So to suppress the dark matter plus, so there's two numbers here, right? There's basically, let's call it, oh my goodness, let's call it like D plus D bar, and there's D minus D bar, right? And in the case of freeze out, D plus D bar is the total abundance, D minus D bar vanishes. In asymmetric, this thing is supposed to be much, much larger than that, so that we actually have a net dark matter number. If that's true, then processes which have dark matter and anti-dark matter talk to each other have to be very efficient, or they have to be have large interactions or probably strong interactions to be able to suppress the symmetric abundance. This is also why it's actually difficult. So if you try to do this with just sort of weakly coupled particles, it's very difficult because typically weak couplings will also lead to a symmetric abundance. So that's why that makes this difficult. Whereas the strong side, usually it works. You can make it work. That answer. All right. Okay. So you see the overview of the mechanisms. All right, let's now, what did I do? There it is. Okay, let's build a model. So, the archive has failed. You have no access to any papers, and your advisor's on vacation, and you want to build a model of dark matter. So you're not going to just go look something up, but you're going to just write down something simple and see where it takes you, right? Okay, we want to build a model of dark matter. Well, we could build a model of any of these mechanisms of dark matter, but unfortunately, I can only build one in the time that I've got. So that's fine. Let's just build one and be happy. Okay. Let's build a WIMP. So a WIMP, a weakly, sort of quasi-weakly interacting massive particle using freeze-out. Okay, so I go back to the previous lecture and I look at all the requirements that I have for it. Electric charge, vanishingly small. Self-interactions, not particularly large. Right? So at that point I might say, okay, no problem. There's a fermion, it's neutral under the standard model. There, I'm done, I've got dark matter. Obviously that doesn't work, right? It might be a good dark matter candidate, but it doesn't talk to the standard model, so there's no freeze-out abundance. Okay, so that doesn't work. Okay, let's add a neutrino. Well, if I add a right-handed neutrino, it's the same thing as this. So I'm basically out of luck. And if you're thinking, oh yes, but there's this tiny Yukawa coupling, it's too tiny, forget it. Okay, it's not going to work. Okay, let's do a left-handed neutrino. Well, now I'm suddenly stuck. Now I have to be careful. I can't just add a left-handed neutrino. I've got to add L, which is E. Let's call it, I don't know, what do we call this? Okay, let's call it L and new L. There we go. Which is not to mean any of the leptons or neutrinos of the standard model. Okay, so now at least this thing, this new left, there we go. This left-handed neutrino is certainly talking to us through the Z interaction. Great. There's another particle around which I have to do in such a way that I could sort of put this into a doublet. Okay, and now I can go and compute, abundance. But right away I'm stuck. Right away I have problems because if this thing talks to the Z, then I know I already have a LEP constraint from Z invisible Z width into neutrinos. So that tells me that the mass of this thing has to be above 45 GeV. Okay. Maybe that's not so bad, right? 45, yeah, 45, that's fine, sure, that's okay, that will work. So you can go and proceed and try to go off and compute this thing, and then after you go through the process of computing the abundance and figuring out what mass it works, you'll find it looks like freeze out is going to go, and we can get this to make. And then you go off and tell your experimentalist friends, aha. Dark matter, it's just a neutrino that's heavier than the Z. Okay, you can find it, no problem. It's got a full strength Z coupling. And so then they will go off and look at your wonderful new L. You tell them it has a full strength Z interaction because it's a neutrino, and they will scatter this off some nucleus. And they'll say, well, what's the rate? You say, no problem, I'll compute it for you. So the per nucleon scattering cross-section, the cross-section of the Z off an individual nucleon, and then I sort of do a coherence over the number of nucleons that I've got. So really the Z is coupling off the entire nucleus, but then we turn that into an effective interaction onto just a single nucleon. So, and then you compute this number, and you find it's approximately 10 to the minus 39 centimeters squared, with some dependence on the mass, but okay. And they say, great, we can measure that cross-section. So they go off, they do it, and this, in fact, they did exactly that. They've gone off and measured this thing, measured the cross-section. And the per nucleon cross-section today, the latest constraint from Xenon 1 ton, I believe, looks something like this. Okay, so where this is approximately 30 GeV, down here is approximately, say, 5. Way out here is about a TeV. And they get an exclusion curve. They say, we have not seen anything up here. So all of this is excluded. Right? All of that's excluded. You say, well, that's no problem because 10 to the minus 39, where is that? Where is that on here? Relative to the latest experimental data, it's up here. This number is 10 to the minus 47 centimeters squared, roughly. A few, like 5. Okay, if you really want a number, something like that. So it's excluded by 8 orders of magnitude, at least at 30. Well, okay, we didn't need it at 30. We wanted this maybe 100 GeV. Shift up to 100, it weakens to maybe instead of 5, 10 to the minus 47, it's like 10 to the minus 46. Still ruled out by 7 orders of magnitude. You could say, oh, okay, well, okay, screw you, experimentalists. I will solve this problem. I will just keep raising the mass of this thing, you know? We'll just crank this thing up, put it up to a TeV. Well, it's still ruled out now by 45. That's 6 orders of magnitude. Okay, 1 TeV, fine. Okay, I don't know why I'm going to put this thing so heavy, but instead of making 1 TeV, I'll make it 3 orders of magnitude is a PeV. 3 orders of magnitude beyond that, I don't know what it's called. So let's call it 10 to the 6 TeV. EV. I give up immediately. I can't do it. So, right, it's 10 to the 6 times heavier than this scale, and then finally, it could be allowed.
But so the generations of neutrinos are 3, so that we know by cosmology, no?
We know light neutrino species are 3. We don't know about heavy ones. Light relativistic, well, quasi-relativistic neutrinos. So there's 2 problems. One problem is I already told you there's a bound, but I haven't told you where it came from. So I'm already violated my bound to try to make this work. So that this already doesn't look good. There's another reason, which is, and this is something we should have recognized from the beginning, I can't just add a lepton doublet. This is anomalous under the standard model. I had to add also a quark doublet. So, you know, T prime, B prime. Not only that, these are chiral fermions. Chiral fermions do not get mass. So I said I was going to give this thing a mass of 100 GeV, but how am I giving it the mass of that? So clearly, even this content, this neutrino should have been massless. That's what we said from the day one, right? Day one we did neutrinos, and we said standard model neutrinos are massless. Well, this should have been massless, so I can't even give it a mass. Doesn't look good, right? All right. Well, you can solve that problem by adding a right-handed neutrino, and you give it a Dirac mass. Right? That's a simple thing to do. We talked about Dirac masses. We could do that. But then I still need these quarks, and now I have to do something to give them mass. So I either have to give them Yukawa couplings. So I either do this story plus new right, and then this story. So in other words, let's do this new right down here, all right? So I add basically a 4th generation of fermions plus a new right. This pairs up with that. That gives me a Dirac mass, and then I just give Yukawa couplings to all of these things. There's 2 problems with that. First, we haven't seen top primes or bottom primes at LHC. That's a serious problem. There's another problem. These things will contribute to electroweak precision observables, such as the one that we talked about on Wednesday, second lecture, BW3 mixing, or otherwise known as the S parameter. Because the S parameter was always just adding up the number of chiral fermions we had in our theory. So if I add a whole another generation here, I'll have to stick that in there, and it's not looking good. Okay. Well, that sucks. All that work for nothing, right? No, we can, okay, yeah, we're model builders, we're strong. We don't need advisors, we don't need papers to figure out what to do. So, okay, here we go. So erase that, we have to leave that. We clearly don't want a Z interaction. That's bad, right? If we do that, we're sunk. But this notion of trying to be minimal, of just having, like this with a right-handed neutrino, that's kind of nice. But the problem is that if I just do this content, quarks, schmorks, we don't want extra quarks. So if we do this, this looks okay, but it has the anomaly problem. But wait, supersymmetry solved my anomaly problem for me. I had a Higgs, it had the same quantum numbers as a lepton doublet. And what did I do to solve its anomaly problem? I just added an uptype Higgs and a downtime Higgs, and they're Higgsino partners. So I could do the same thing here. So I have an L and an L prime, and now I've got an L prime. Oh, I don't know how to draw this, but okay. Anyway, it's fine. And then L prime, something like that. Where, to be clear, so this thing is in a 2 1/2 representation. This is in a 2 minus 1/2 representation. And so whether you want them this way or flipped, okay, let's not get into that. That's just fine. Okay, maybe I should flip them. Let's flip them. All right. So let's give this sort of nu prime, L prime. So one of these is a lepton of +1 charge, and one of them is a lepton of -1 charge. And now I can write a mass term, L prime, a vector-like mass that will marry all of these fields off. If I solve my anomaly problem, got a vector-like mass. Okay, we got rid of the quarks. We solved that problem. There could still be potentially, well, fine. Yeah. Okay. Okay. So then, what else? What else do I need to do? Well, I'm after this state, right? I'm after one of these two states, and right now it looks like, right now this is looking like I'm creating another Dirac fermion after all of nu and nu prime. Well, if I have a Dirac fermion under SU2 cross U1 with these quantum numbers, it's going to have the same problem with the Z. The Z will be there. I can't get right. But it's Dirac fermion, it's Dirac, it can have a conserved quantum number, it's going to couple. The Z, that's very, yeah, frustrating. Okay, well, but we can again go back to neutrinos for our solution to the Z problem. We could give these neutrinos a Majorana mass. Now at first, we can't do it directly because nu and nu prime, right, are fields that transform under SU2 cross U1. So I can't just directly give it a Majorana mass. But we talked about the Weinberg operator, which in this context would be L H. Let's give this a new name. This is smelling too much like a lepton. So let's call this D and call this D prime. And we'll call this D plus and D minus and D0 and D0 tilde. So you have no confusion that this is possibly a lepton anymore. I could do this. Okay, so I could add into my theory. Now, D has the problem, it looks like a derivative, but anyway, that's fine. There's no index on there, okay, so it's not a derivative. All right, so it's the D field contracted with this, and I also have potentially a D prime contracted with H dagger, and I may or may not have got the dagger straight. Let's do it this way. So I add Weinberg operators in this effective theory, and these will lead to Majorana masses for D0 and D0 tilde. So if I write out the mass matrix for this, I have D0, D0 tilde, D0, D0 tilde, and what do we put in here? Oh, I don't like it this way. Let's do it this way. If I do it that way, then you can see that this vector-like mass here, let's call it big M, goes into the diagonal parts, and then whatever these coefficients are, let's call them C and C prime, I get C V squared over lambda, C prime over lambda. And I may have mixed up where the prime goes, but it doesn't matter. This is not the seesaw formula, by the way. The seesaw formula would not have had a term here, and that's what caused one heavy eigenstate, one light eigenstate. This has in both components. So what this is doing is taking a Dirac fermion and splitting it ever so slightly into two Majorana states. Okay, so I don't know whether I want to call them like D10, I don't know what to call them, D01, D02, or something like that. And the splitting is given by just this this piece here. So it's basically the splitting is given by approximately c plus c prime b squared over lambda. Okay. Now, my dark matter, which was previously a Dirac fermion and had a full strength coupling to the Z, is split into two states, of which the Z is only able to talk to the 2 and 1 state.
What are the components of D and D prime? It's like, it's too much chalk to read it.
Yeah, too much chalk. Here, let me rewrite it. Yep. Hopefully I write the same thing. So there's a D plus and a D0, and then there is a D minus and a D0, call it tilde. So these are the charged states, the lepton-like objects, and these are the neutral states, the neutrino-like objects. I give it this Majorana mass that splits the two D and D tilde into two mass eigenstates. I don't know what I want to call them, so let's just call them D01, D02. I'll eventually drop this notation by this amount, right? By this amount of splitting, and the interactions that we have are that. So now the Z interaction talks to D02, D01. Okay, but in the early universe, whatever the mechanism of this of freeze out, which we're going to have to look at, we'll look at this in just a second. However this is going to work, this state, as long as this mass splitting is even larger than some, reasonably finite value, this will eventually decay back into that on a time scale of the on shorter than the age of the universe, typically much shorter. So you're only left with one state. So the dark matter is only made up of the Majorana state, and then this is gone for this light state. D01, D0. Okay.
There's no Z interaction?
There's no Z interaction with a Majorana particle. The would-be Z interaction that was there with the Dirac fermion talks to D01 and D02, the light and the heavy state, not the light state. Majorana fields carry no conserved quantum numbers. It can't possibly interact with a vector boson.
But I don't understand when you say it's Majorana, because D not and D not tilde, they are Chiral, right?
So these are two
Chiral fields.
These are two Weyl fields. Yeah, these are all Weyl fields. Yeah. So these are two Weyl fields that would normally have married off to become one Dirac fermion, but in this case they're split because of these interactions that I've written down. Okay, so we have now, all right. We're getting there. Don't you worry. Don't worry, Matthias. It's coming. I mean, time dependent, it's coming. Okay. Okay. There's no tree level interaction. Good. Okay. All right. So now you can ask the question about, well, what about, what is the abundance of this thing? I mean, we said we're going to do freeze out. What is it? That presumably will set something to do with our mass scale, M, big M. And here, this scale will be set by, well, it just shouldn't be so narrow so as to somehow reintroduce an effective interaction with the Z and nucleus. And, okay. Maybe just one quick point, which is, what are the masses of the charged states? Well, they're also, right, just sort of right here. They're right here with this Dirac fermion. They actually happen to get an additional small contribution from electroweak breaking, but it's a finite effect. And it's a finite effect that typically raises it so that, I mean, this is not to scale, but in effect, up here is where the D plus D minus states sit. And of course, they're charged, so it still has to be, of course, a Dirac fermion that marries them off, right? So the spectrum of this theory is a single, after electroweak symmetry breaking, the spectrum of the theory is a single charged state and then two neutral states split by this amount. There are still, so this transforms under SU2. So SU2 means we certainly have interactions of the type W, D plus, and D0, or some combination of D01 and D02, right? So let's just write this as 1 and 2, some combination of that. Right. Okay, so we certainly have these interactions, which means that if we go early enough in the universe, the W will talk to the standard model bath, and that will populate these species. Right? Through what? One obvious thing to do would be okay. The W's talk to D0, 1 or 2, D0, 1 or 2 here, with D plus as an intermediate state. The strengths of these interactions is G, the usual electroweak strength G. And aside from having to take into account that there's multiple channels, it's a relatively simple process to go and compute. And you compute the annihilation rate of this, and you find that it is approximately G to the 4th, 22 pi. All right. I almost had that. M squared. Yeah. Let's write it that way for now. Okay. So there's phase space. There's some number that I've sort of absorbed inside of 22. It's not really 22. It's some approximate number like that. The G to the 4th, of course, is just this quantity squared. It's a very simple Feynman diagram process, all for, you know, and of course this is thermally averaged in the early universe. The cross section, of course, has to have units of 1 over mass squared, and the only mass scale in this problem is big M squared. Okay. So that's what it is. Then you can go and compute what is the relic abundance of this wonderful dark matter candidate. And you find that that is 2 times, let's just get the scaling right, yes, M over 1.1 TeV squared. Okay, I included the H here. That's the conventional thing to do. If you don't want H, just there's a 0.7 squared. You divide across, you get 0.25 on this side, as you like. So when M, big M, is about a TeV, we get the right abundance. That wasn't so hard. Model building's easy. Now you just start with some fermions, okay, you do this, you look at the constraints, you rule things out, look at the next thing, it's not yet ruled out, compute the abundance, okay, so now we have a mass scale to shoot for. That also tells me where in this plot I'm gonna have to be concerned with, right, which is gonna be right here, okay, when I come to finally figuring out what the scattering rates are. All right. Right away, there's one lesson which may or may not be so relevant these days. However, it used to be said that it was natural, quote unquote natural, for WIMPs to be sort of at the 100 GeV scale. Here is a particle who has a full strength weak interaction to us, and its mass is 1 TeV. It, in fact, was never the case that 100 GeV is where you expected weakly interacting dark matter to be. You always expected it to be at the TeV scale. And if you think this is an anomaly not a real anomaly, not a technical anomaly, colloquial anomaly, if you think this is an anomaly due to somehow some choice of what I did, no. I could have done a different model which had, instead of 2 doublets, but a single triplet, and redone the same calculation, and I'd get a number here that's more like 2 or 3 TeV, depending on the details of the calculation. So the TeV scale was in fact always the scale we should have expected for dark matter that thermally froze out with full strength interactions to the weak scale. Okay. The only reason people ever really thought it might be lighter is, well, if dark matter is somehow connected to this solution to the hierarchy problem or that solution to the hierarchy problem, we always had some imagination that the hierarchy problem would be solved at the 100 GeV scale, and so what you do is you start playing games and tuning couplings and so forth, and eventually you can get 100 GeV. But actually the TeV scale is what you should have expected. Okay. Now, that's just, I mean, this is just nature, right? If we want to match it, this is what we get. Which is frustrating, because how are we going to see this? Well, okay, we can produce various combinations of these states through Drell-Yan production, either through the photon or through the weak interaction. Let's just draw one of them. I'm not saying this is the dominant one, but I just want to illustrate what this looks like. Okay. So there, I produced the charge states. That's great. But the charge states decay down to these light states. And they decay through W emission. But this splitting, I didn't tell you what it was, but the splitting turns out to be I'll just tell you the number. The splitting turns out to be 340 MeV. And you're like, what? Where did that come from? Okay, it's a finite correction from electroweak symmetry breaking. And really the exact number is typically in the range of hundreds of MeV, and it's really just, anyway, it's coming from ratios of the electroweak scale divided by the dark matter. So it's of that size.
So it does not depend on C and C prime?
So the assumption here is that this splitting is much, much smaller than that splitting, although it's true that if this splitting is larger, then there can be potentially a narrower gap, yes. So that, you're correct that it is possible for these states for there to be a potentially narrower splitting between one set to another, but for now I'm actually assuming this splitting is much smaller than that, just for fun, okay? It could also be the other way around. It actually could be that you can, if this scale is not that much heavier than the TeV scale, it could be that this stays actually up here or up here. And then you're back to 340. Okay, so there is sort of maybe one special tuned place for this scale where these actually look like I drew them, even though I probably should have drawn them like that, so as to not induce the question. But you're correct that it could have been that way. Yeah. Okay. Good. So these things will then go back down to one of the D0 states. They'll decay down and emit a W, quote unquote. But 340 MeV is certainly not producing an on-shell W. For that matter, it's not even producing many quarks. Right? There's not much you can decay into. The dominant thing is actually to sort of go into a pion, right? Although, of course, it could also go into very, very low momentum leptons. Right? That's a possibility as well. And now you go and ask your LEC experimentalists. I have a process. Drell-Yan production of charged states that are 1 TeV that decay with 2 pions, or maybe really, really weak, really low energy leptons. And let's say, right, no way. No way, they can't do it. Well, they can sort of do it. They can sort of do it. But the way in which they do it is, they say, forget about this. Well, yes, not entirely forget about this. They care about these, okay. So the would-be dark matter states escape the detector as missing energy, so that's nice because that's a background reducing technique. But they have no hope of trying to see this stuff, so they don't even try. But 350 MeV is a splitting such that right this decay down in this way is moderately suppressed, and so the lifetime of the charged states is not incredibly tiny. It is sort of finite. In fact, the decay length is sort of in maybe the ballpark of a centimeter, which is not too bad. So they have tried to do this type of thing. And let's do it as lifetime. And 0.02, 0.3. This is in nanoseconds. And the bound looks something like that. And the scales are 100, 200 GeV. And this 340 MeV, well, there's one small subtlety to this. This 340 is the number that you get when you asymptotically take the mass significantly larger than V. As you take the mass closer to V, there are some other effects that it changes the exact splitting. It actually gets a little bit narrower, which is good for them. So that there's sort of some weak dependence on that, and they're able to get a bound here at about 150 GeV. So LHC can actually search for this process when these states are about 150 GeV. At 150, they're sufficiently, there's a sufficient production cross-section, and this decay length is just sufficiently long. They can look for these stubs of the tracks, and they're able to get a bound of 150, which is pretty good. That's better than LEP, right? LEP is only ever able to do 100 GeV, because it's pair production. So they're making progress, but 150 is unfortunately far away from 1100. And unless someone comes up with some super creative thing that they think that could work, LHC is hopeless for being able to directly produce and try to see these states, because it's heavy.
What about monojets?
Again, it's because it's weak production of these states. The difficulty, so with monojets you look for large missing energy, but you tag off something else like an ISR jet, right? That's what you're thinking. But because the rates here are electroweak production at a TeV, it's too small. So that's the problem. So monojet is also a process that is used to try to constrain these things. My understanding is that this is the best bound. I don't know what the number is off the top of my head of monojet reinterpreted here, but it's not much different from this. Okay.
So could you maybe again explain this diagram? I didn't.
Sorry.
It's on the y-axis and.
So on the y-axis is the mass. Sorry, I'm below the unitarity bound here. So it's the mass on the y-axis of the charged states. Remember that these other states are split by something that's much smaller than any of the scales I'm dealing with here. Their bound is to rule out always above this curve. Okay, they rule out above this, and what's above this are lifetimes longer than 10 to the minus 2 nanoseconds or 10 picoseconds, right? So they're able to rule out between 10 picoseconds up to whatever this is, 300 picoseconds. And then you can take those times and turn that back into something. And the prediction, sorry, I should have drawn this in a different color. The doublet prediction for what the splitting would be is about here. As I said, there's a weak dependence on the mass, but this eventually asymptotes to a lifetime that is the lifetime you compute given that splitting. Okay. Good. Okay. Well, it's depressing for LHC, but okay, maybe that's just life. Surely, direct detection is going to help us. We just have to figure out how it's going to work. Unfortunately, one of our advisors was already in the room and told us. Matthias just told us there are loop contributions in which we could, instead of going through Z, we go through some pair of W's. This is by no means the only process that is possible. You could also, let me erase this. Okay, you could also have done, for example, Higgs exchange. Okay, something like that. There's Z exchange diagrams as well, because now the Z could go between the 1 state to the 2 state and then back down to the 1. So you can do Z box diagrams. So that's great. So we can estimate the size of this. If you do this diagram, you would estimate that the cross-section, sorry, the per nucleon cross-section would be whatever we had before and with its suitable scalings times g squared over 16 pi squared from the loop. And then we have a Higgs interaction with the nucleus. So that's basically roughly M nucleus over something heavier. Let's call it maybe the mass squared. Something like that. You might think at first that, well, I did the Higgs diagram. The Higgs has a small coupling to the nucleons. I go over here, the W looks like it has a full strength interaction with nucleons. So surely this must be larger. That turns out not to be the case, because the effective operator by which this matches onto in the nucleon in the non-relativistic effective theory involving these nucleons is actually quote-unquote twist 2, which means there is a momentum suppression. And the momentum suppression basically ends up being something that has the same form as if the Higgs were talking to the nucleon. So this is the going rate. It's this, and then there's a small enhancement basically due to sort of numbers of diagrams, sort of on the order of 3 squared. Anyway, all of these are just approximations. If you go and you turn the crank on this, you find that the going rate for this process is about, for any one of the diagrams, the going rate is about 10 to the minus 47 centimeters squared. So this is the loop factor plus sort of this additional suppression. Okay, and I think this is actually should be V, but anyway, it's fine. So the 10 to the minus 47 is now this line, but it's at a TeV, so it's here. This differs from the current bound, or the best bound that we know now, by approximately 100, maybe a little less, maybe 50. So it's about 50 times away. The current constraint is about 50 times away this 10 to the minus 47. Which at first seems like, that's not too bad. Except that I said that this process, this is the going rate for sort of one of the diagrams. When you add up the diagrams, there is a notorious cancellation with the Higgs, which happens to be right where this particle is approximately 125 GeV. It's one of those accidents of numerical whatever you want to say, and so that the actual per nucleon cross-section of all the diagrams, you okay? Yeah, I know, that's depressing to me too, okay, is less than 49. And this was most clearly pointed out by a paper by Hill and Solon in about 5 or 6 years ago. And they take into account many of they do the calculation very carefully. They match the non-relativistic effective theory carefully. And they also concern themselves precisely with some of the nuclear uncertainties of these scattering matrix elements to try to understand what the systematic uncertainty in that is. And they're basically getting sort of these numbers. Now, so whether the number is this or even smaller is not precisely known, because it depends on these details. But now that's another 2 orders of magnitude below here, and that's actually below what's known as the neutrino floor. The neutrino floor in direct detection is the floor at which atmospheric neutrinos produced by cosmic ray collisions in the upper atmosphere. They produce a flux of neutrinos. These neutrinos can coherently scatter off the nuclei of a direct detection experiment, and the going rate for that here is probably about at this point. So below this, it means you have a background of coherent neutrino scattering, which just makes the process of finding this that much more difficult. Yep.
So you get minus 49 because you have suppression between the different channels?
Between the different diagrams.
Okay.
Yep. An example where the suppression doesn't happen is if you do the same calculation, not for a doublet, but for a triplet state, something that is a 3 under SU2, then you find that, again, the going rate is the rate that you get. It is 10 to the minus 47. Okay, so that is the cross-section. So, okay. So, all right, our wonderful doublet model of dark matter has the correct abundance when it's 1 TeV. It is completely safe from LHC searches, basically because of its mass being 1 TeV, which we should have expected from the beginning because of the weak strength interaction. And its direct detection scattering cross-section is there through a loop diagram, but is highly suppressed. So, this could be dark matter. I don't know. I mean, we don't know. And it's going to be a long time before we figure out whether this really is or isn't. But you see, we didn't have to do that much to make this go, but we did have to do a few things. Maybe the one piece of this that should trouble you more than anything else is, these terms, they look weird. I had to add dimension 5 terms to do that. Well, it's not weird in the context of neutrinos, right? Again, if I had just, since I started with neutrino physics and I started writing down Weinberg operators, you were already used to seeing these things. But if I had just done this without that, it might have been a little bit more strange. However, there is a ultraviolet completion of all of this theory, which is, of course, when these doublets are, in fact, exactly the Higgs-Xenos of supersymmetry, and these operators are generated once you integrate out gauge-Xenos. So you get exactly this theory in a supersymmetric completion. So this is otherwise known as Higgsino dark matter, although that's the first time I used that word. You can just think of it as doublets with this Majorana splitting. So anyone who tells you WIMPs are dead or WIMPs are highly disfavored because of we haven't seen them in direct detection and we haven't seen them in LHC, it's obviously wrong. I didn't do much. We constructed the whole thing in just half an hour, right? Didn't have to do much. Well, okay. To be fair, this may be a somewhat special theory. At least it's special because of this cancellation making this very small. However, as I said, there are other versions of this where you can take a triplet or even more exotic representations of SU2, and most of the story goes through, except that then there are other indirect detection constraints that are disfavoring those theories, which is why I didn't talk about them. Okay. All right.
So can indirect detection probe that scale of mass?
Can you, sorry, what?
Indirect detection, can it probe this model?
Can indirect detection probe it? Yes, and so one way to probe it is to have this diagram proceed in the galaxy nearby, ideally, and you annihilate dark matter into W's. The W's will then decay into stuff, and you can hope to try to see that stuff. Which stuff you look for depends on the best ratio of signal to background. Probably the best stuff to look for are photons. Now, obviously W's are not photons, but W's can certainly emit photons as FSR radiation, but even better is W's will fragment into quarks, quarks go to pions, pions go to photons. You integrate over the flux of those photons, and that can set a constraint. Unfortunately, that doesn't set a constraint in the Higgsino case. It does set a strong constraint in a different model in which you have a triplet. Okay. And that's actually work that my colleague Tim Cohen and his collaborators realized also about 5 or 6 years ago. Okay? So 1 TeV works. Now that I have this annihilation rate sitting here, we can address the issue that is erased, but that's okay. We can address the question of how heavy I can make dark matter. Okay. So let me just do that here. So I had up here 100 TeV. I said that was sort of an upper bound. You can see if I stare at this annihilation rate, okay, I need to, cosmology is demanding that this abundance be omega h squared is about 0.1. The scaling is mass squared, like this, right in the numerator, which came from 1 over the annihilation rate, right, which is here. So this is the process that would happen if I have electroweak strength and a mass. But I could ask the question of, well, suppose I kept on increasing the mass and I generalized beyond the electroweak coupling to something else. So now I want to imagine, for fun, there's some annihilation process of into, and I want to allow myself for the strength of this coupling to grow. So then you can see here, I need to keep g to the 4th over m squared constant. Right? If I keep that constant, then I keep this constant. So if I increase the strength of the coupling, I have to increase the mass. But there's a limit. For the effective theory to be valid, I certainly couldn't take this coupling beyond 4 pi. Right? Once it goes to 4 pi, then I no longer have an effective theory I can perturbatively calculate. Right? So the effective theory will certainly break down by the time this thing gets to be over 4 pi. And so then that tells me a scale of the mass, a mass which is then constrained effectively by the theory becoming strongly coupled. Right? The different way to phrase that, the way to phrase theory is becoming strongly coupled is, for example, when people worried about whether the Higgs was there or not there in the Standard Model, they worried about the unitarity violation of WW scattering. Right? You keep on increasing the energy of the process, and then eventually WW scattering becomes non-unitary. So analogously here, we could have a scattering process. And if we keep on increasing the coupling, it'll eventually become non-unitary. So we can compute the mass at which that happens. So that is what is known as the, if I can spell their names right, Grist Kamyankov. S-K-Y-I-I. Grist-Kamyakovsky unitarity bound. It's very simple in principle. So I compute, and I find that the bound is 2j plus 1 pi over p squared. This is the bound for a certain annihilation, or a certain cross section with spin j, or in the jth channel. It turns out that this is basically dominated by j equals 0, or at least you can compute this for j equal to 0. The momentum here, for our purposes, is something when this freezes out, it freezes out non-relativistically. That's what it means to be freeze out. So our momentum is non-relativistic. So this is basically m v rel, the relative velocity of these guys, divided by 2. You turn the crank on that, put it in here. So you get sigma v rel is got to be less than 4 pi over m squared v rel. Relative velocity. You can take typical relative velocities of the early universe, right? These things freeze out at a temperature of a factor of 10 or 20 or so below the mass of the particle, and then just directly compute what the bound on the mass is, and it is 4 pi over sigma v rel v rel all to the 1/2. So this is what I need to get that number, roughly a picobarn. VREL is some fraction of 0.2 or 0.3 or something like that. And you get, okay, with an uncertainty of probably at least a factor of, tens of percent. All right. So roughly speaking, if we take dark matter above 100 TeV and then its annihilation rate would have to be sufficiently strongly coupled that it would be right near the perturbative estimate of the unitarity bound. Okay, so this is the analog of how heavy can we make these states. This is the analog of how heavy can we make the Higgs state to still unitarize WW scattering. That's 1 TeV. This is 100. Okay. So that should give us hope, at least from the perspective of, well, okay, I mean, if I imagine dark matter is in fact strongly coupled, then I could, it could be this heavy. This is depressing from sort of an LHC point of view, because you may not be able to produce it directly. But on the other hand, if it's actually realized at some very large scale, it has to be strongly coupled. So that gives hope that there is some couplings. It's not some super weakly interacting thing. It's not just purely gravitational. So it might give hope. It gives hope to try to find it. Typically, the theories that will end up here are strongly coupled dark matter theories. So composite dark matter and so forth. These will tend to end up in this sort of territory. And there are actually theories that are already being probed here through lower dimensional interactions in direct detection. Okay. So that's the unitarity bound. That's 100 TeV. That's as high as you can go from thermal freeze out into an individual particle. You can, of course, imagine that particle has strong interactions with other guys and basically does fusion and creates these massive nuclei. That can push you above the 100 TeV scale. Yeah. Okay. Good. So, doing this WIMP story might feel slightly depressing to you, like at least in the sense that, okay, so the WIMP still works, it's fine, it's just this particular version of it is going to take a long time before we'll actually have evidence as to whether it's true or not, and may require a future collider to be able to begin to probe these things. The fact that there is all of these different mechanisms for dark matter production, axions, misalignment mechanism, and freeze in and freeze out gives opportunities for lots of different kinds of experiments. And that's one of the things I would say that's really ongoing in the field of BSM physics is to either invent new ways to search for dark matter in these pockets of mass space or coupling space that could be there, and also repurpose experiments that we already have to be able to probe these things. And that's already happening. For example, the Xenon experiment was originally, Xenon experiments were always designed to have dark matter scattering off the nucleus, but they are in fact are setting among the best bounds on dark matter electron scattering. So, and that it would be applicable to dark matter that's relatively light, between say the electron mass up to maybe GeV or so, when nuclear scattering is happening. And people realized that approximately, 8 years ago or so, and they took the information and repurposed it, and now papers are being published by the Xenon collaborations to go and precisely do these kinds of measurements and to look for it. So it far from this sort of work suggesting that, oh yes, okay, I don't know what's going to work, anything goes. No, in fact, you can do a lot of creative work in trying to uncover what you can and can't find in an experiment, and that makes it interesting. You may also have had the impression that, we talked about the hierarchy problem, but of course the LHC is already probed to beyond 100 inverse femtobarns and not seen new physics. We've probed the Higgs boson in great detail. We have not seen deviations of Higgs couplings. We've looked for dark matter below the neutrino scattering cross-section of 10 to the minus 39 centimeters squared by 8 orders of magnitude and have not seen anything there. And that might give you some pause as to what one could or should be working on. But I want to end with one sort of provocative sort of statement or note, but it has to do with some physics. Okay, so when I got into the field in the mid-90s, there was lots of excitement in lots of different areas in phenomenology as well as in formal theory, and there was this problem at that time, which was called the age of the universe problem. The age of the universe problem was that astronomers were looking out into the universe, and they would have techniques to measure the ages of stars and ages of galaxies. And when they did these measurements, looking deep into the universe, they would get numbers on the order of, or up to on the order of 12 billion years. They would say 12 billion years is what we see. We see objects in the universe that are 12 billion years old. At that time, in the mid-90s, the cosmologists were saying, these guys, they don't know what they're doing, they have systematics, they're wrong. We know the universe is 10 billion years old. We just compute it, no problem. Dark matter, it's 99% of the matter, or 97% or whatever it is. 3% of it is baryons, there's a tiny percentage in photons today. We just go and directly compute the age of the universe. That way we get 10 billion. And not only that, but even if the universe is not exactly of critical density, even if it's much smaller than that, go and recompute it, you get even smaller ages. So these guys are wrong, systematics, no way. Okay? And then supernova were uncovered. They looked for type 1a supernova, expecting to see deceleration, right? Expecting to see the deceleration of the universe, and they saw the opposite. They saw acceleration. Acceleration, which could be elegantly explained by a cosmological constant, even if it is fine-tuned, could be elegantly explained by a cosmological constant that when you put the constant in and you go and compute the age of the universe, which probably Laura did for you, I don't know if she did, maybe she did, you get 13 point whatever billion years. Just long enough to accommodate exactly those observations that the astronomers were saying are there. Today, we have a discrepancy between the Hubble constant, as measured by astronomers, 73, 72, there's various numbers, lots of different techniques. The measurements have been going on for a while. They have these very creative, elaborate ways of getting it, right? They first measure, they use parallax to measure some object nearby that they understand, say like a Cepheid star. Parallax gets you a reliable measurement there. Then from that you use the Cepheids to go out a little bit further to sort of nearby galaxies which also happen to have a type 1a supernova. You go out that far, then you calibrate your type 1a supernova to the Cepheids. And then from there you can bootstrap that out even further to further type 1a's. And you measure the Hubble flow, you measure the Hubble constant, and you get this 72, 73 kilometers per second per megaparsec, right? These are the units. Planck, WMAP before it, and Planck satellite now, has done fits to the cosmological model, and they find 67. So, and the error bar, now, okay, if the error bar were, 5 or 10 kilometers per second, there would be no discrepancy, we wouldn't care, we'd say, whatever. But each group is claiming an experimental uncertainty that is sufficiently small that these things are sufficiently separated that it makes you wonder what's going on. And a very common refrain that I hear is, oh yes, but the astronomers, it's systematics, they don't know how to do this, it's clearly cosmology is going to be right, the CMB will be right, and it's 67. But exactly that incorrect thinking was there because very few people had really seriously thought about modifying cosmology so as to accommodate the data. And so it may be that this discrepancy now is on the threshold of uncovering a new fundamental difference in cosmology, which may have to do with dark matter, may have to do with dark energy, may have to do with nothing. We don't know yet, but it's worth at least thinking about. Yeah. So, find your own adventure and don't always listen to your elders. And I think you'll do well. So that's it. Thank you.
Yeah, thanks.
Thanks, Graham, for very lively and excellent lectures. Some more questions? Exhausted. Yeah, there's one.
Xenon model form in the thermal universe in the early.
So it's just it thermal freeze out. So that's precisely what we were calculating here. So it has interactions with the W's. The W's talk to the standard model plasma. So yeah. So it's all in thermal equilibrium at high temperatures, and then it just freezes out. It's very it's comparatively simple.
In supersymmetric theories, the dark matter must be the lightest stable superquanta. Is that right?
Correct.
Are there any problems making this Higgs Xeno that the lightest?
I would say it's just a parameter choice. There's problems depends on what you mean by a problem. Obviously, to make this go, it has to be 1 TeV. And the thing that I mentioned yesterday was that to achieve the weak scale in supersymmetry, you needed to tune the supersymmetry breaking contribution to the uptype Higgs mass squared against the mu parameter. I used mu yesterday. Mu there is big M here. So if this is 1 TeV, then I've clearly got at least a 1% tuning just to get the dark matter to go. Not even to say anything about cancellations. So that's an example of something. There's a tension. Yeah.
Yes.
Yeah. What are the prospects of detection of this candidate of fusion colliders? Do you need a proton, an electronic machine, or could the leptonic one test it?
Well, a leptonic one would presumably need to be above 2 times the mass of this
by indirect
thing.
precision testing.
I don't think I'm not aware of any indirect precision test that will give you easy access to this. It has been studied at 100 TeV proton-proton machine, and the numbers there, which with great respect to those who computed those, because they're trying to do something that's far beyond what we're doing now, they were getting numbers of being able to probe 700, 800, 900 GeV, depending on details. Close, maybe not all the way there. I mean, it seems like I think if you let's put it this way, if you're going to if this one of these projects gets closer to on shell, I'm sure there will be considerable additional investment in trying to push that all the way up to the 1.1 TeV level. But it may require creative ways, creative techniques in the detector strategy to be able to find it.
Okay, so that is again the end of the lecture by Graham. Thanks a lot, and we'll break the session.